In the last lecture, we looked at the Newton-Euler formulation. The basic idea in the Newton-Euler formulation is propagation of velocities and accelerations from the base link to the free end, and then we use the Newton's law and Euler's equation to compute F equals ma and torque equals I alpha plus omega cross I omega, and then we propagate these forces backwards to the base. And to find the joint torque, we take the z component of the moment. In this lecture, we look at another way to derive the equations of motion. This is called the Lagrangian formulation. The Lagrangian formulation is an energy-based formulation. It involves obtaining the kinetic and potential energy of the rigid body or a system of rigid bodies. We can derive the Lagrangian formulation from the Newton's law and Euler's equation. This involves advanced calculus of variation and something called as the principle of least action. We will not prove how to derive the Lagrangian formulation from Newton's law and Euler's equation. So as I said, the Lagrangian formulation involves evaluation of the kinetic energy and the potential energy. The kinetic energy of a rigid body I with mass mi and inertia I with respect to some fixed coordinate system can be written in this form. So the first term is half mv square. Basically, we find the velocity of the CG of any link of mass mi and then do b dot v. Likewise, we find in the second term the angular velocity of link I or rigid body I, and then we multiply with inertia matrix, so I into omega I, and then we take the dot product of this with omega I. So this is the expression for the kinetic energy of a rigid body I with mass mi and inertia I with respect to a zero or a fixed coordinate system. The first and the second term from the linear velocity of the center of mass and angular velocity of the rigid body, as I had explained. Again, just to reiterate, 0 VCI and 0 omega I are the linear and angular velocities of the center of mass and rigid body I, respectively. The 0 VCI is nothing but the I VCI. If you recall, in the propagation equation, we obtained I VCI, but pre-multiplied by a rotation matrix. So I VCI is the velocity of the center of mass described in its own coordinate system. Likewise, the angular velocity of rigid body I in some fixed or zero coordinate system is also obtainable from I omega I, which was again, if you recall, was involved in the propagation equations. So you take I omega I and pre-multiplied by 0 I rotation matrix. And I omega I was also nothing but the angular velocity of rigid body I described in its own coordinate system. So using the above equations, we can show that the kinetic energy of rigid body I, instead of writing VCI0, we can write IVCI dot IVCI, because this is basically a scalar, which is the magnitude of the velocity. This is also a scalar, which is magnitude of the velocity of the center of mass. So it doesn't really matter whether we are obtaining it from in the zero coordinate system or in the ith coordinate system. And the same story is, instead of obtaining half 0 omega I dot 0 II 0 omega I, we can also obtain the kinetic energy as half I omega I dot Ci I omega I. Okay. So as I have mentioned, we can use the velocity propagation formulas for serial chains. So, and recall that the angular velocity of the ith link written in its own coordinate system can be written in terms of the angular velocity of the I minus 1th link, the previous link, again written in its own coordinate system, pre-multiplied by this rotation matrix. And if it is a rotary joint, then we have to add theta dot I along the z-axis. So this is what the rotary joint is adding to the next link. The angular velocity of the next link is the angular velocity of the previous link plus what is happening at the rotary joint. If it is a prismatic joint, then the angular velocity of the I minus 1th link is same as the angular velocity of the ith link. The velocity of the center of mass of the ith link can be obtained by the velocity of the origin plus some omega cross r, and here r means IPCI. So this IPCI locates the center of mass with respect to the origin of the ith coordinate system, or the origin of the ith rigid body. And we could do this from I equals 0 through n, and we can obtain the kinetic energy of all rigid bodies in a serial chain. Okay, so all we need to do is half mvci square plus half omega dot I omega. If you have parallel chains or configurations with loops, then no such propagation formulas can be used. Okay, so in that case, we go back to our basic definition of what is velocity, which is basically in terms of derivatives of the position vector or derivatives of the rotation matrix, and then we can obtain the angular velocity of any link in a parallel chain as r dot r transpose. Okay, this is 0 means it is with respect to the reference coordinate system or the fixed coordinate system. Likewise, we can obtain the velocity of the center of mass of any link in a parallel chain by taking the time derivative of the position vector of the center of mass. And again, this position vector of the center of mass can be obtained by loop closure equations or by techniques of kinematics for parallel chains. Okay, so 0 PCI is the position vector of the center of mass of link I. The other element in the Lagrangian formulation is the potential energy of a rigid body or the system of rigid bodies. So when we want to compute the potential energy, the main assumption is in this formulation, the potential energy is due to gravity alone. If you have springs or other energy storage devices, we need to modify the potential energy term. So for example, if you have a spring, which is a torsional spring, then we have to add one term half ki theta I square, where k is the spring constant. So, but most of the time, or at least in this lecture, we will assume the potential energy is due to gravity alone. The general expression for potential energy due to gravity is nothing but mgh. Now, instead of writing simply mgh for any link, we write it in a more formal form as dot product of the gravity vector with the vector locating the CG of the link. So PCI locates the CG of link I, Mi is the mass of the link I, and then this gravity vector dot this will give you the potential energy. Minus is because the gravity is normally acting in the downward direction. Okay, so gravity is along vertical direction, which is the z-axis, but the gravity is in the opposite direction. The magnitude of this gravity vector is 9.81 meters per second square. And as I said, 0 PCI is the location of the center of mass of rigid body I from the 0 or reference potential energy surface. In potential energy, often this notion of a reference or a 0 potential energy surface is used, okay, to find the value of the potential energy. In this formulation, we'll see it really doesn't matter where you choose this 0 or potential energy surface, because whatever it is, it's a constant value, and later on we'll see in the Lagrangian formulation, we have to take the derivatives of the potential energy. So derivatives of some constant quantity will go to 0. And so we should not really be worried about what is the reference or the zero potential energy surface you have chosen. So once we have the kinetic and potential energy, we define a scalar quantity called the Lagrangian. Okay, so this is the symbol for Lagrangian, this L. It will be a function of Q and Q dot. So Q's are the joint variables or any other generalized coordinates which you use to describe this serial or parallel chain. Q dots are the derivatives of the generalized coordinates. And this Lagrangian is nothing but Ke minus Pe. So for each link, we find Kei and potential energy of ith link. Then we subtract these two and then we sum over all the n links which are part of the rigid body chain. Okay. So in this case, this n does not include the fixed base. Okay, so because the base is not moving. So in serial manipulator with R or P joints, the dimension of Q is nothing but n, which is the number of joints. Okay, and this is also same as capital N in this example. In kinematics, if you recall, this capital N was the number of links, but we have to add the fixed base. Okay, so in the planar 3 degree of freedom robot, we had 3 moving links, but capital N was 4. Here we don't do that. Okay. So the equations of motion, once you have this Lagrangian, is given by d by dt of partial derivatives of dl by dqi dot minus dl by dqi. This is equal to qi. Okay, so let's go over this term by term. So this is partial with respect to qi. So the Lagrangian will be a function of both the generalized coordinates and also the derivatives of the generalized coordinates. Remember, the potential energy will contain only some position vector, so it will be a function of qi. But the kinetic energy will be a function of q dots also. Okay, so we also need to take the partial derivative of this Lagrangian with qi dot. Okay, and then time derivative of the whole thing. And this term in the left hand side is now equated to what is called the generalized forces. So Q, capital Qi are the externally applied generalized forces. And how many of these things do we have to do? We have to take I equals 1 through n. Okay, so where n in this case of serial robots are the number of links, okay, moving links. When only joint torques or forces are present at the links, so there is no other external force which is being applied, the capital Qi will be nothing but the torque supplied by the motors or at the joints. So after performing the derivatives, the equation of motion of a serial chain takes this form. Okay, so we find the Lagrangian, we take the partial with respect to Qi, then we take the partial with respect to Qi dot, and then d dt of that one, and then if you add up do all these things for I equals 1 through n, and then simplify, then we can rewrite the equations which you have got in this form. And this is a well-known form. Okay, we have seen this earlier also, that we get in something called mass matrix MQ. So this mass matrix is only a function of the generalized coordinates Q. Okay, it's an n by n matrix. Q dot is n by 1, and then we have another term which is C into Q dot plus G Q equals tau. Okay, C Q Q dot is also an n by n matrix, and then this matrix into Q dot is an n by 1 vector of centripetal and Coriolis terms. This Coriolis term and centripetal term contains only quadratic terms. So you will have Qi dot, Qj dot. You will not get qi cube or qi dots into q2 dot square. Okay, so it is only quadratic terms. The right hand side is an n by 1 vector of joint forces or torques. This term gq is what is called as the gravity term. Okay, this is only a function of the position of each link. It is not a function of the derivatives of the generalized coordinates. The equation of motion of any serial chain can be written in the above form. This is a very, very important statement. If you give me any serial chain, okay, then it can be written in this form, that there will be a mass matrix into q double dot, then there will be a Coriolis centripetal term, then there will be a gravity term, and which is equated to the torques which are acting at the joints. Let's look at some of the properties of the terms in the equations of motion. The most important property of this mass matrix is that it is always positive, definite, and symmetric. And how do we prove that? You can show that the total kinetic energy of a serial chain or any serial robot is given by Ke is half q dot transpose m into q dot. So this is a quadratic form. It is of the form x transpose ax. The kinetic energy is always greater than 0 for q dot not equal to 0, and 0 only when q dot is equal to 0. M of q is positive definite. This implies that. Okay. Another way of looking at it is inertia cannot be imaginary along any component of q double dot. Okay. So basically eigenvalues of mass matrix MQ must be real and MQ must be symmetric. Okay. If it were not symmetric, then the eigenvalues could be imaginary, which doesn't make sense. Okay. It is also positive definite because the inertia can never be negative along in any component of q double dot or any direction. The Coriolis and centripetal term can be obtained from this mass matrix, which is M, and we take Mij and then take the partial derivatives with Qk. Then you take Mik partial derivative with Qj and minus Mkj Qi. Okay, so we take all these elements of this mass matrix and take appropriate partial derivatives with respect to Q's. Okay, and then you sum it over from k equals 1 through n. Then you multiply it by q, sorry, before you sum it over, you multiply by q dot k, and then you sum it over k equals 1 through n and into half. Okay, so where does this formula comes from? You can show that this is indeed true. Okay, this is sometimes in advanced math it is called as a Christoffel symbol. So it comes from that notion that you have something which is positive definite, which is mass matrix. So it is related to some kind of a metric or a distance in some q space, and then in that, with that mass matrix, okay, or with that metric, positive definite metric, we can define something called Christoffel symbols, and they are nothing but these components of the centripetal and Coriolis terms. Okay, the gravity term can be obtained as partial of potential energy with respect to Qi. Remember, gravity is only a function of the position. It is not a function of q dot. If you have loops as in parallel configurations, then we can get this M loop closure constraint equations. Okay, so I have some loops. There are M such loops. Okay, so our M loop closure constraint equations. Each loop can have more than one loop closure constraint equation. So let's take the situation when in a parallel configuration we have M loop closure constraints equations. So what are these? These are some eta I of q equal to 0 and I equals 1 through m. So in such a situation, the dimension of the generalized coordinates is n plus m. So we have n actuated joint variables, typically denoted by theta, and m passive joint variables, which we will denote by phi. Okay, and to obtain the equations of motion for a system with constraints, so basically we have kinetic energy, potential energy, but then we have these loop closure constraints for the generalized coordinates. So then we can use what is called as a Lagrange multiplier. This is very well known technique. It is available in many textbooks. So for example, in Goldstein or by Hogg, that we use this notion of Lagrange multipliers, and then we can derive a new Lagrangian, which is called L, and notice this bar on top. So this is a function of q and q dot, which is same as the original Lagrangian, which is kinetic minus potential energy, minus this sum over j equals 1 through m. So there are m loop closure equations. So n of j, so this is like constraint, into some lambda j. So these are called as the Lagrange multipliers. So those of you who have done any optimization course, you can see that when you want to optimize an objective function with some constraints, we introduce those Lagrange multipliers. Okay, and this is the same idea. So the Lagrangian, we can introduce these Lagrange multipliers and with this loop closure constraints, and we form a new Lagrangian, and then we can go ahead and derive the equations of motion. So if these m constraints are holonomic, which means only functions of q, okay, then the equations of motion are given in this form, which is that you find the partial with respect to qi dot, then take the time derivative, and then partial with respect to qi, and then this is equal to tau I, which is the joint torque, plus this term, which is some j equals 1 through m lambda j into partial of this loop closure constraint equations with qi. And now I will go from 1 to n plus m. So remember, there were theta actuated joint variables, which we denote by theta, and there are n of those, and then there are phi's, which are the passive joint variables which are not actuated, and there were m of those. So in matrix form, this equations can be written in this form. Again, we have a mass matrix into q double dot plus some Coriolis centripetal term into q dot plus some gravity term. This is same as the joint torques, but now we have another matrix which is psi transpose lambda. Okay, so what is psi? Psi comes from here, partial derivatives of loop closure constraints with qi. So nj with qi, you will get a matrix which is this psi, and then this can be written as psi transpose lambda. So in this equation, we have lambdas, which are the Lagrange multiplier. There are m of these Lagrange multipliers coming from the m constraint equations, and then this constraint matrix psi of q is obtained from the partial derivatives of the m constraint equations with respect to qi. So if you do this and rewrite, we can see that this could be written in this form. So the lambdas are unknown as of now. We need to derive the lambdas in order to find the equations of motion. So the lambdas have been introduced by us. So we need to find what the lambdas are. So to obtain the lambdas, we twice differentiate the m constraint equations with respect to t. So once, if you differentiate eta of q equal to 0, you will get some psi into q dot is equal to 0. Then if you differentiate that again, then you will get psi into q double dot plus psi dot q dot is equal to 0. where psi dot is an m times n plus m matrix containing the time derivatives of each of the elements of this constraint matrix psi. So now, since the mass matrix is always invertible, okay, so we can rewrite q double dot as m inverse tau minus cq dot minus g plus m inverse psi transpose lambda. Okay, where is this coming from? This is coming from the equations of motion. The equations of motion were mq double dot is equal to tau minus cq dot minus g plus psi transpose lambda. So we pre-multiplied both sides by m inverse, and m inverse always exists because the mass matrix is positive, definite, and symmetric, and always invertible. So once we have this q double dot, we can substitute this q double dot back into this constraint equation, which we have differentiated twice, and then you can see that you will be left with only lambda. Okay, and if you do some simplification, you will get lambda in this complicated form, which is some psi m inverse psi transpose the whole thing inverse, and then the psi dot q dot, which is coming from here, and then psi into m inverse and tau minus cq dot minus g, okay, with a minus sign. And finally, we can substitute this lambda back into this equation, and we can get equations of motion. Okay, the form of the equation of motion is like this. We have m into q double dot, which is f minus psi transpose psi m inverse psi transpose the whole thing inverse. Quite complicated, but if you do and sit down and write it down, you will get this, because what is happening, we can substitute lambda here, so you will get some m inverse psi transpose this whole thing, which is this minus term, and so on. Okay, it is not very hard. And then we have this another term, which is psi m inverse f plus psi dot q dot. So psi dot q dot is coming from here, and then psi m inverse f, this is f is this tau minus cq dot minus g. Okay, we already have some m inverse, so we will get this term psi m inverse f, and where f denotes tau minus c q dot minus g. Okay, so let's see what has happened. So we have done a lot of algebra and lot of simplification to arrive at an equation of motion which is of the form mq double dot is some tau minus c q dot minus g plus this whole big term which comes from the constraint matrix. So intuitively you can see that if we did not have loop closure equations, if it was a serial chain, we didn't have to bother about this Lagrange multipliers, we didn't have to bother about this constraint matrix, then this part will not be there. So you will be left with mq double dot as tau minus cq dot minus g, which is the same as what we obtained for the serial chain. Okay, but because of the presence of loop closure constraint equations and constraint matrices psi, okay, we will get this complicated term. We'll see some examples of this later on, how we can use these loop closure constraint equations and obtain this constraint matrix, and then obtain this equations of motion. So let's look at some of the properties of this equations of motion. First thing is that the mass matrix M is now n plus m into n plus m. So n are the actuated joints, which is theta, m are the passive joints, which comes from the loop closure constraint equations. Even then, it is a positive, definite, and symmetric matrix. The centripetal Coriolis terms and the gravity terms are n plus m times 1. Okay, in the case of serial robots or serial chains, we had n cross n mass matrix. The centripetal Coriolis term was n cross 1, but now we have to take into account the m loop closure constraint equation. So hence the dimensions get modified in both of these terms. The term psi transpose lambda as units of torque or force. Okay, so these are called also constraint forces and torques. Okay, why has this units of torque? Because if you just go back one more slide, you can see that it was tau plus psi transpose lambda. So tau has units of torque or force. So hence this will also be similar units. Okay, this constraint forces, one of the interesting property is that the work done by the constraint forces is zero. Okay, so how do I find out what is the work done by these constraint forces? So it is nothing but some force times velocity. So we have psi transpose lambda, whole thing transpose into q dot. That is the work done by these constraint forces, and that we can simplify. So A into B whole transpose is B transpose A transpose, so which is lambda transpose psi q into q dot. But we know this psi into q dot is 0 because psi into q dot comes from taking the first derivative of the loop closure constraint equation. So since if this is 0, then the work done whole thing is also 0. It is useful to obtain constraint forces and torques for mechanical design of joints and rigid bodies. So although they do not appear to add to the work done or to the kinetic energy of the system, okay, but we still need to know what are these constraint forces. Okay, the whole idea is similar to what we had looked at in the Newton-Euler formulation. Not only we need what is the torque due to the motor, but we also need to know what are the reaction torques. In this Lagrange formulation, the same reaction torques and forces appear as constraint forces and torques. Okay, not exactly the same numerically, because in the Newton-Euler formulation, the constraint forces were along x, y, z. Okay, so remember fx, fy, fz, and nx, ny, nz. Here, the constraint forces are along the generalized coordinates q. But nevertheless, the q's and the Cartesian coordinates and orientation can be related. So most multi-body dynamics software packages, for example Adams, okay, compute and provide the constraint forces and torques. Okay, so this Adams is 2002, but there are now newer versions of Adams, and we will see one such newer version later on. But the feature in Adams or any other multi-body dynamic software packages, you can obtain the constraint forces and torques. In mobile robots and few other mechanical systems, sometimes the constraints are non-holonomic. Okay, so what do we mean by non-holonomic? They are not only functions of the generalized coordinates q, they could be function of q dot, and we cannot get rid of the q dot, so they are non-integrable. So in the example of that rolling disk, thin disk, I showed you that the constraints are in terms of the velocity at the point of contact being 0, and hence the constraint contains both q and q dot, and we could not get rid of the q dot by integration. Sometimes the constraints can also be functions of time, explicit functions of time. Okay, so in such systems we can also use the Lagrangian formulation. So the general constraints in what is called as the Pfaffian form, okay, Pfaffian form, is phi of t is psi into q dot equal to 0. So psi into q dot was similar to what we obtained by taking the derivatives of the loop closure equations. So sometimes the constraints could be directly in the form of psi into q dot and non-integrable. And this term is showing the explicit function of time. So we can have constraints which have as an explicit function of time and then involves q and q dot. So we can differentiate this constraint to get psi into q double dot plus psi dot q dot, so which is coming from this term using chain rule, and phi dot of t equal to 0. Then the equation of motion can be modified and we can obtain the equation of motion if the constraints are given in this Pfaffian form, that it is given by mq double dot is equal to f minus again this whole complicated term which is psi transpose psi m inverse psi transpose the whole thing inverse, then psi m inverse f. But now we have terms which are phi dot of t and then this psi dot q dot was earlier also there. And lambda now is also now can be obtained to include the effect of phi of t. Okay, so lambda will now contain phi dot of t. Previously this term was not there. So as I said, these are non-holonomic constraints. They are non-integrable functions of q and q dot. They restrict the space of q dot but not the space of q. Let's now look at an example. Okay, we want to derive the equations of motion of a planar 2R manipulator. We have done this earlier. We have looked at this system, two rigid bodies connected by two rotary joints. We used a long time back how to obtain using Euler's equation and Newton's law. Then we also derive this equations of motions for this system using the Newton-Euler formulation. Now I want to show you that we can derive the equations of motion of this 2R system using the Lagrangian formulation. Okay, so it is the same as the example done for Newton-Euler formulation. We have two moving bodies, two joint variables theta 1 and theta 2, two joint torques tau 1 and tau 2 which are acting in this form counterclockwise positive. The first link has m1, I1, R1 and L1. So m is the mass, I is the z component of the inertia, R locates the CG of this link 1 and L1 is the length of this link. And the same story with the second link. There is a gravity which is acting in the minus y direction, and m, I, R, these are denote the mass, length, CG, location and the z component of the inertia matrix. This is a planar example, so only IZZ is relevant. So we can use the propagation formulas to find the linear and angular velocities. So because it is valid for this serial chain also. So with 0 as a fixed coordinate system, and that is fixed, so hence the angular velocity and the linear velocity is 0. So for I equals 1, we can find 1 omega 1 which is 0 0 theta 1 dot, 1 v 1 0, and the linear velocity of the center of mass is given by some 0 r1 theta 1 dot 0. Okay, so this is quite obvious. So the first link is rotated in theta 1. So the CG is located at a distance r1. So that is r into theta 1 dot, and it will be along the y direction, which is what is shown here. For I equals 2, we can show that the angular velocity is theta 1 dot plus theta 2 dot along the z axis. The velocity of the origin of the second link is given by L1 S2 theta 1 dot, L1 C2 theta 1 dot 0. Okay, this is nothing new. All of these were done when we did the Newton-Euler formulation. And the velocity of the center of mass is the velocity of the origin plus omega cross r. R is R2 0 0. We have assumed that the center of mass is along the link. Okay, along the x-axis, local x-axis. So the total kinetic energy is nothing but half mv square. So one term from v square will give this I theta 1 dot square, then I theta 1 dot plus theta 2 dot square. So this is the kinetic energy due to the rotation of the first link. This is the kinetic energy due to the rotation of the second link. And then we also have this kinetic energy of the second link vc2 dot square. So m2 into velocity of the center of mass of the second link, square of that. And if you simplify this, and we have done this earlier, you will get one term which is L1 square theta 1 dot square. There is also R2 square theta 1 dot plus theta 2 dot whole square. And then 2 L1 R2 C2 theta 1 dot into theta 1 dot plus theta 2 dot. Okay, so we have done this earlier. This is nothing new. It is very simple conceptually. We are doing the kinetic energy of the first link plus the kinetic energy of the second link, and we know what is the angular velocity of first link, and we know what is the angular velocity of the second link, and similarly what is happening to the center of mass, linear velocity of the center of mass of first link and the linear velocity of the center of mass of the second link. Okay, so for rigid body 1 we have these two terms. Okay, for rigid body 2 we have these two terms, the second, third and the fourth term. The total potential energy is nothing but mgh of the first link, and again if you go back and see what is the height from the reference, which is the x-axis, it is r1 into sine theta 1. So we have m1g r1 sine theta 1. The second link, the distance from again the horizontal, is L1 S1 plus R2 S12. So the Lagrangian for the planar 2R manipulator is given by kinetic minus potential energy. In this case, I am using capital theta to denote the generalized coordinates. The generalized coordinates are theta 1 and theta 2. So this Lagrangian is a function of theta 1, theta 2 and theta 1 dot, theta 2 dot. Okay, so you can see theta 1 dot, theta 2 dot. Similarly, there is a theta 1 here. This is sine theta 1. This is sine theta 1 plus theta 2. So the partial derivatives of this Lagrangian with respect to theta I can be very easily obtained. You take the partial derivatives and you will get one term which is minus m1g r1 c1 minus m2g l1 c1 plus r2 c12. The partial derivatives with respect to theta 2 will be a little bit more complicated. We will of course have this gravity part which is m2g r2 c12, but we also have terms which are coming from c2 into theta 1 dot and then theta 1 dot plus theta 2 dot. Okay, so in the kinetic energy there was a term which contained c2 into theta 1 dot whole multiplying theta 1 dot plus theta 2 dot. So when you take the partial derivatives of cosine, you will end up with minus s2. Okay, so this term will also come. The partial derivative of this Lagrangian with respect to theta 1 dot and theta 2 dot can also be obtained. So the partial with respect to theta 1 dot will contain I1 plus I2 plus m1 r1 square and so on, and then into theta 1 dot. There will be a term, as I said, which contains m2 l1 r2 c2. Okay. And then of course there is this other term when you take partial with respect to theta 1 dot, which is I2 plus m2 r2 square and so on into theta 2 dot. The partial of Lagrangian with respect to theta 2 dot is a little bit simpler. Okay, but nevertheless we have a term which is m2 l1 r2 c2. Okay, and then of course I2 plus m2 r2 square into theta 1 dot and I2 plus m2 r2 square into theta 2 dot. Okay, so this is very mechanical. So once I know what is the linear velocity of the center of mass of each link and the angular velocity of each link, I can find the kinetic energy, And then if I know where is the center of mass with respect to a reference, so I know the height, so I can find out like mgh, and I know the potential energy. Then I combine both of them as Ke minus Pe, which is the Lagrangian, and then mechanically take these 4 partial derivatives, one with respect to theta 1, second with respect to theta 2, then with respect to theta 1 dot, and then with respect to theta 2 dot. And then we have to take the time derivatives of these two quantities, which is what the Lagrangian formulation says you have to do. Okay, so we take the time derivative of this Lagrangian, partial Lagrangian with respect to theta 1 dot, and when you take the time derivatives, you will get some terms which are containing theta 1 double dot, but then we also have time derivatives of C2. Okay, so you will again get some theta 2 dot into sine theta 2, so which is what these terms are. So the time derivatives of theta 1 double dot is this plus this into this, theta 2 double dot into this, and then we have some m2 L1 R2 S2 theta 2 dot into 2 theta 1 dot plus theta 2 dot. Okay, so there is some terms which are like theta 1 double dot into something and theta 2 double dot into something, but then you will get some terms which is 2 theta 1 dot theta 2 dot or theta 2 dot square. The time derivative of the second part, which is Lagrangian with respect to theta 2 dot, partial Lagrangian with respect to theta 2 dot, again you will see some terms which are theta 1 double dot into something, theta 2 double dot into something, but then you will also have a term which is theta 1 dot theta 2 dot. Okay, so then we collect this term, and then the partial of Lagrangian with respect to theta 1, partial of Lagrangian with respect to theta 2, collect all of these terms according to the recipe given in the Lagrangian formulation and simplify. And once you do all that, I have skipping a few steps, you can show that the equation of motion is tau 1 is theta 1 double dot into something plus theta 2 double dot into something, and then you will get this m2 L1 R2 S2 theta 2 dot square plus 2 theta 1 dot theta 2 dot, and then we have these gravity terms which are coming from the partial of the potential energy with respect to theta 1 and theta 2. So we will get one term here, gravity, another term here, and for the second equation again we will have theta 1 double dot into something plus theta 2 double dot into something, and then theta 1 dot square and m2 R2 G C12. So if you go back and open your notes and see what we did for the Newton-Euler formulation, equations are exactly same. Okay, so there is absolutely no difference between the equations of motion which you obtained from Newton-Euler and or from this Lagrangian. So if you rewrite in the standard form, you will get tau 1, tau 2, which is a vector, 2 cross 1 vector, is some matrix into theta 1 double dot into theta 2 double dot, plus this Coriolis centripetal term, plus this gravity term. So in this equation, this 2 by 2 matrix is called the mass matrix as before. This 2 by 1 vector, which is quadratic in theta 1 dot square, theta 2 dot square, and theta 1 dot theta 2 dot, is called the centripetal and Coriolis term. And the last term, which is a function of only theta 1 and theta 2, is called the gravity term. The Lagrangian formulation does not include any friction or dissipative term. Okay, the Lagrangian is for only conservative system. Historically, Lagrange was a mathematician in the 1700s, and he was studying the motion of the planets. Okay, so hence he derived a way to derive the equations of motion, but there is no question of adding friction. So because these are for this Lagrangian formulation inherently is only for conservative systems. So let's take some example. So we have this very well-known example of a simple pendulum. Okay, we have looked at this earlier. So we have a gravity vector like this. This is an x and a y axis. This is the origin, and this is this link and a mass with endpoint xy. Okay, we will see what this L theta dot and other things come, and we have this gravity which is mg. So we recap that the choice of generalized coordinate is non-unique. Okay, so we could consider q, which is the generalized coordinates, as x comma y, which is the Cartesian coordinates of the mass of the bob. The gravity is in the minus y direction. But if you choose xy as your generalized coordinates, then inherently there is a constraint, which is what? That the distance of this point x comma y from the origin is governed by x squared plus y squared minus L squared equal to 0. Okay, L is the length, this length here. If you take the double derivative of this function f of xy equal to 0, you will get x double dot plus y double dot plus x dot squared plus y dot squared is equal to 0. Okay, it's not at all very hard. So the first derivative will be 2x into x dot plus 2y into y dot is equal to 0. If you take the derivative again, you will get this. Again using chain rule. The kinetic energy of this mass is nothing but half m x dot squared plus y dot squared. Okay, so this is a massless rod of length L. So the kinetic energy is only half mv squared. The potential energy is mgl into 1 minus cos theta. So we take some reference here. So this is mgl into 1 minus cos theta, whatever is the height above that reference. The Lagrangian is nothing but kinetic minus potential energy, and just by following the Lagrangian formulation, we can obtain the equations of motion of this simple pendulum. And what are the equations of motion? Sort of obvious. We have mx double dot is equal to lambda times 2x, and my double dot is minus mg plus lambda times 2y. Remember, there are no forces or any torques which are acting. The only external force is due to gravity. Okay, so hence, and this is acting along the y direction. So we will have some component of this external force, gravity, in the y direction. And this lambda times 2x and lambda times 2y comes from the derivative of this. Okay, so as I said, you will get 2x into x dot plus 2y into y dot. So that 2x and 2y we need to multiply by lambda, because the constraint is, remember the constraints are psi transpose lambda. So we will get these two terms. So let's continue. So I have two equations of motion. One of them is x double dot is lambda into 2x by m. And the other one is y double dot is minus g plus lambda into 2y by m. So let us substitute this x double dot and y double dot into this, and we solve for lambda. Okay, basically similar to what I showed you, what we do when we have loop closure constraints. In this case, the constraints are that x squared plus y squared minus L squared is 0. And this is the second derivative of the constraints. So if you substitute lambda into 2x by m and minus g and so on into this expression, we'll get 2 lambda by m L square y into g minus x dot square plus y dot square. Okay, so this is what you will get. So to interpret lambda, what does this lambda mean in this problem, or in this case of this simple pendulum? So we can see here that we can also define this x and y by using this L and theta. So we can set x is some L sine theta. This is x coordinate, which is this distance, perpendicular distance, that is L sine theta, and then the y component, which is in the negative direction, is minus L cos theta. Okay, so we can set these two by introducing a variable theta, which is from the vertical, and this length L. So if you substitute x and y and then x dot and y dot and x everything into this expression here, you will see you will get 2 lambda by L into L, 2 lambda into L is minus ml theta dot square minus mg cos theta. Okay, so x dot square plus y dot square will be what? It will be something like L theta dot square. Okay, so L square theta dot square, and then if you simplify and then if you do some simple algebra, you will get this expression, which is 2 lambda into L is minus ml theta dot square minus mg cos theta. So this is what is shown in this figure here. So we have, this is mg, the direction of motion of this mass is L into theta dot. So this is like the tangential velocity. This is the velocity of the mass instantaneously. Due to this velocity, we have some ml theta dot square, which is acting outwards, and also mg cos theta, which is acting this. So those of you who remember your basic mechanics, you can see that this mg cos theta and ml theta dot square is nothing but the tension in this rope or wire. Okay, so both of these terms have units of force. Okay, and they are along the wire. That is important. So hence this 2L lambda is the tension T in the wire. Okay, so in Newton-Euler formulation, we could have found this tension by seeing that there is an mg here, there's an mg cos theta here, and then there is something else, and then there are all these mg sine theta and so on. Here it is a little bit more complicated because we need to find what is the Lagrange multiplier, and then this Lagrange multiplier is related to this tension in the wire. So this is like a constraint force. And again, remember, tension in the wire is not, it's an internal force. It is not doing any work. It is a constraint force. But we can still find out what is this constraint force. So the purpose of this example is that I could have chosen a different generalized coordinates, in this case x comma y, for this pendulum, and then we have this constraint, which is x squared plus y squared is L square. Okay, and then due to that constraint, just by following the Lagrangian formulation, we can find an expression for the Lagrange multiplier, and that Lagrange multiplier is related to the constraint forces. In this case, there is a nice interpretation of what exactly is the constraint force. It is nothing but the tension in the wire. So the velocity of the mass is in this direction, L theta dot. It is tangent to the motion, and hence the work done by this constraint tension in the wire is also zero, because these two are always perpendicular to each other. Again, everything is consistent with whatever I showed you mathematically earlier. I showed you that lambda into psi transpose, that part, the work done by psi transpose lambda was zero. Here also, we know for a simple pendulum, we have studied this in many places, that there is something called the tension in the wire, and that is perpendicular to the direction of motion, and hence the work done by this force is zero. Okay. So in summary, the equations of motion for a serial or a parallel configuration and multi-body system, even with non-holonomic constraints, can be obtained using the Lagrangian formulation. The equations of motion obtained using the Lagrangian formulation does not contain friction or any other dissipative term. Okay, the Lagrangian formulation is for conservative systems only. However, in any mechanical systems we have friction, and how do you accommodate that? We just add it in an ad hoc manner. So originally we have tau is m into q double dot plus c q q dot gq. We just add a friction term. So this friction could be a function of q and q dot. So if you just write it like this, then you can think that this centripetal Coriolis term and this friction term look more or less similar, but that is not true. This is quadratic. This friction could be quadratic, but it is very different from the centripetal Coriolis term. Okay, this is a dissipative term. Typically, this friction term is some constant times some function of q dot. Most of the time, linear function of q dot. So this friction for tau 1 will be c1 plus c2 into q dot or theta 1 dot. Okay. So one part which is called Coulomb friction, one part which is called viscous damping. This is a typical model for friction. And note that this friction, this is quadratic, this is not typically not quadratic. The other disadvantage of Lagrangian formulation is that this equation of motion does not contain the effect of flexibility, backlash and other unmodeled dynamics. Okay, so people are worried about what is happening to the energy which is going into the flexibility. So if there is a deformation, okay, so something called strain energy might be happening. Okay, we can have backlash between the gears which are there in the motors. So we cannot model all these effects in Lagrangian formulation.